So in the second video, we'll be talking about rounding errors, which are a little bit different, but they still involve how binary numbers and decimals are related to each other. So with rounding errors, this has to do with fractions. So when I introduced you to decimals and binary numbers last class, I talked about the fact that, if I had 314.159, even the place values to the right of the decimal point are really, so I had 1/10, 1/100, and 1,000ths. And these are really still powers of 10. They just happen to be negative powers. Well, this happens in binary also. So if I have 0, 0, 0, 0, 1, 0, 0, 1, oops, I'll say this is, I'm still going to use 1 byte, but we're going to pretend the decimal place is here. Well, if I wanted to change this into decimal form, a decimal number, a base 10, this is my 2 to the zeros, which is 1. So that's 2, 4, 8, 16, 32, 64. Well, this would be 2 to the negative first, which is a half, or 0.5. So this number as a base 10 would really be 4.5. Again, our standard is still 1 byte. If I move the decimal place somewhere else, and I say, well, I have 0, 0, 0, 0, 1, 0.01, well, now here's where my ones are, or 2 to the zeros, 2, 4, 8, 16, 32. This would be my 2 to the negative first, which is 0.5. And this would be 2 to the negative second, which is 1/4, or 0.25. So this number as a base 10 would be 2.25 in base 10. You don't actually need to know how to do fractions in binary, but it's the same way we do fractions in decimal. Now, please note I'm calling them fractions and not decimals, because decimal is built upon the idea of base 10. So even though I have what we call a decimal point here, when I'm in binary, I'm going to call them fractions. And the point is just showing where the fraction part starts. The key idea of rounding errors is that what I have right here, we cannot express every fraction as the finite sum of powers of 2. The calculus teacher in me said I had to include the word finite in there. If we go far enough in powers of 2, eventually we could write any fraction. But a computer can't devote that many bits, an infinite number of bits. So there are only so many bits a computer sets aside for numbers, like we saw with overflow error, which means that even when we have fractions like the red and the black here, there's only so many bits that can be devoted to fractions. Well, not every fraction that's in base 10 can be written using a finite number of bits in base 2. So when that happens, the computer rounds it. It says, what's the closest I can get to that fraction? And say, okay, that's good enough. So like here, 0.39 or 39 hundredths is going to be somewhere between 0.5 and 0.25. So even though these are really just 1 decimal off, because this, oops, changed to a pen. So if I switch to 4 bits, a nibble here, this is the same as 0.5 in base 10. And this is 0.25 in base 10. I can't use more bits very easily here. So somewhere between these has to be the 0.39. Well, we say, okay, well, what if we have it as, okay, it has to be a little bit bigger than 0.01. What if I say it's 0.011? Well, that's a 0.25 because this is 1/4, which is 0.25, and this is 1/8 to the negative third, which is 0.125. So I get 0.375 in base 10. Well, that's pretty close to the 0.39. And I could keep trying. Well, what if I add another one there? Well, that's going to add 0.0625. And I'll get closer to 0.39, but I'm never going to get exactly 0.39. I'll get something close by the time I run out of bits. So for example, if I say, well, okay, let's go with 0.111. I'm sorry, 0.0111. Well, I have 1/2 plus 1/4. I'm sorry, let me start that over. My brain is not working properly right now. I have 1/4 plus 1/8 plus 1/16. And all of this will give me 0.3, oh, sorry, 0.3, and then I have 5, and a 2 is 7, 6. Well, my brain just decided it's done for the day. So if we simplify this, I will get something close to 0.39, but I've now used all 4 bits that I had set aside for a number. I don't really need the leading 0 here. I've run out of bits to use for a fraction. This is as close to 0.39 as I'm going to get. So the computer's going to say, you know what? This is close enough. So while you mean 0.39, I'm going to use this instead. And you're going to have a rounding error. In terms of avoiding rounding errors, it's just like avoiding the overflow errors. We need more bits to represent the number, specifically the fraction. Drawback, same as before, costs more money if you want to add more bits to the device. Or if you're not adding more bits to the device, you have to take the bits that are being used for something else, and that may slow the device down. So overflow error is all about I don't have enough bits to represent large numbers. Rounding error is I don't have enough bits to get the exact fraction value, so I'm going to get as close as I can and realize there's a small error.